Hello, how are you? I want to continue talking about recursion. Now, the last time I sent a video your way, I was looking at a binary tree. And again, this is an example of a binary tree. It's a binary search tree. As we've said before, notice, Casey is less than Dylan. Alva is less than Fendi. Fendi is greater than Dylan. Alva is greater than Dylan. But they're all less than Jones. So everything to the left of Jones is less than it alphabetically, and everything to the right of it is greater than it. I put this null here because there was no other way I could show you that there was nothing there. And I think that it works fine. Now I want to add a new function to this. I want to add a function to print this tree. But in the world of trees, binary trees, we actually have three choices of the way we can print this tree. We can print this tree in three modes. Mode 1 is pre-order. In this case, we print the value in a node and then print the left subtree, and then we print the right subtree. Now I think what I'm going to do is move this down a little, and I'll move this over. Now, that's a recursive definition, although you don't realize it probably at this point. So let me show you how this would work on this particular tree. In the tree above, we print the value in the node. So that means we print Jones. And maybe there. Now, the left subtree is a tree starting at Dylan. So we do the same thing we did for the other one. For the left subtree, we print the value in the top node. In this case, that is Dylan. Then we print the left subtree of Dylan. So Now I go down. I was afraid of that. There's not much I can do. Bring this up a little. Bring this up a little, maybe. And I have a few lines here I can bring up. And if I have to, I can make this smaller to get a few more lines. And even here. Now, let's look at it. The left subtree of Dylan has one item in it. So we print the down one, pardon me. We print the value in its top node. So we print Casey. We try to print left subtree. It is empty. So we've finished that. We've gone down that way. Now we print the right subtree. Of Casey. So let's see. The right subtree, now it's the same. Print Fendi. So over here we print Fendi. Print left subtree. Well, that's Elva. So we print Elva. And now there's nobody below Elva. So subtrees of Elva are empty. Well, the last thing we were doing was printing the left subtree. So now we have to print the right subtree. Of Fendi. Now let's see, is there a right subtree? Yep, Hillman. So we print Hillman. Now there's nobody on either side of Hillman. So I will pull this back one line there. And I'm going to bring this down to 16. Now, let's look. Both subtrees are empty. We have done the three things we wanted to do to print the right subtree of Casey. So, pardon me, it wasn't Casey, it was Dylan that we were doing the right subtree of. Pardon me. We printed the value in the node. There was no subtree. Now we wanted to do the left subtree of Fendi, of Dylan, pardon me. That's where we are. If you see, I'm indented from Dylan. I printed its value. I printed its left subtree. Now I'm going to print its right subtree. And then I did all of that. So I've done everything I need to do for Dylan. Now let's see. I printed the left subtree that started at Dylan. And I printed the value in the node. Well, the next step is to go to the other side. So now I print the right. Pardon me, it has to go back one line here. Print the right subtree of Jones. Well, I think that does it. The left subtree, oh, pardon me, I went back the wrong place. I needed to go there. We printed the left subtree, starting at Dylan, and now we're going to finish do the right subtree, and at this point I'm just going to say, etc. So, again, I read this as follows. The output will be Jones, Dylan, Casey, Fendi, Alver, Hillman, Smith, Williams, Townsend, and Zeiss. That is one possible order. Now, let me take this down here. And put it back here. And I'll remind you that pre-order is Jones, Dylan, Casey, Fendi, Alver, Hillman. Then we have to go to the other side, Smith. It has no left child, so we go right. Williams. It has a left child, Townsend. And then it has a right child, Zeiss. So what else could we do? Well, the next possibility is post order. In this one, we print the left subtree, print the value in the node, and print the right subtree. The right subtree. Very minor change, it seems. I'm not going to go through it in detail, but I'll give you what the answer is. Post order is I print the left subtree of Jones. I print the left subtree of Dylan, Casey. I print the right subtree of Dylan. I print the left subtree of Fendi. I print the right subtree of Fendi. I print Fendi. Now I've done both subtrees, so I can print Dylan. Now I have to go to the other side. I go to the tree starting with Smith. There is no left subtree. I have to print the right subtree, beginning with Williams. I have to print its left subtree, Townsend. I have to print its right subtree, Zeiss. I have to print the value in its node, Williams. I have to print the value now in Smith because both his subtrees are done. And now I print the last thing, Jones. So those are another possible way of printing it. There's one more. And if you think about it, you probably can figure it out. Look at what we did. First, the pre-order, we do the node, then left, then right. In post-order, we go left, right, node. Well, we're always going to keep the left before the right. But the one we haven't tried yet is left, node, right. The node is in the middle. So the final one, and the one that actually is used probably more, is this one. Print the left subtree, print value in node, print the right subtree. So in our example, I'm going to have to keep going back. In order is, all right, go left, go left, go left. So it's Casey. Its parent was Dylan. Now, from Dylan, I go left, I go right now. From Fendi, I first go left, so it's Elver. Then Fendi, which is in between them. And then after comes Hillman. And I've done everything on the left subtree of Jones. So now I put Jones in. And now I go right. Yes, right. Smith has no left subchild, so I have to print nothing there. Then I print Smith. Then I go to the right of Smith, Williams. Williams is a left subchild, print that first. Down. Send. Now put Williams in. And finally put Zeiss in. If I were in class, I'd ask you to tell me another name for that order for a binary search tree. You notice it's an alphabetical order. That's why in order is used frequently for when we do binary search trees. Well, if I look up here at all the work I did here, it seems to me that I was recursing all the time. This indentation was one recursion. There was one recursion here. There was a recursion here. It seems like I was always going down and recursing the same way. So I'm going to suggest we do the following as our algorithm. I'm going to write an in-order algorithm. Maybe I'll go to a new page. My in-order algorithm to print a tree, a binary tree. So what I'm going to do is I'm going to say first, I'm going to have an algorithm. I'm going to have something. I will write two parts to this. The first part will be, let me check what name I gave it over here, print in order. It'll be print in, I think I did use, no, in order. Pardon me, I brought up the wrong thing. Print in order. And it's going to be attached to a tree, so I don't have to put anything there. And what am I going to do? I'm going to call print in order auxiliary the root. Now I have to be careful. Root isn't really what I want, because root points to a node. So I'm introducing something here that I've mentioned before, but I need to keep mentioning it. Let's see, how can I do this? I'll go over, make it a side over here. If root has a declaration node star root, which it does, then okay, one more try. Move that over there. Okay. Then asterisk root is a node. It is what root points to. That's I call that deaccessing the pointer. I'm taking the point. I'm taking what was an address, and I'm asking to go to that address. And if you look here, it makes sense, because this says root asterisk is a pointer. It is a node. So star root is a spot here, and that's a type node. Now I had to do that because the next step is going to the print auxiliary is going to be a little bit different. First of all, print in order auxiliary is going to get a node. Notice it is not getting a pointer to a node. At least I don't think it is. Let me check back. I may have written it differently. No, I did write it as a node. It is a node, yes. It's not a pointer to a node. It's a node, which is why I needed the star root. So what am I going to do there? Very simple. First of all, I want to print what's in it. Now I got to be careful here. I don't want to take any chances with having nulls. So the first thing I'm going to look at down here is if the root is null, the tree's empty. So actually I should have done that above that. I really should have done right up here to take a little bit of to have a deficient case. If root is null, print empty tree. Else, call this. Now I have a note, so let's see what I can do. I want to print everything off to the left. So how should I do that? What would happen? Again, I want to take a quick look at my program over here. Yes, that's what I thought. Now, I want to go left, if there's anything to the left. So if no, I'll call it n. It's node n. If n, now n's a node. It's not a pointer. So if its left child is not null, then I do my recursion. I print in order auxiliary the left node n dot child. Now I think that's what I did. I always have to check and make sure I'm not missing something. Yeah, I did it right. All right, so I've done the left child. Print n dot name. In my case, I printed two things. Then, if n dot right child is not null, print in order auxiliary n dot right child, and we're done. That's what's so nice about recursion. I'm done. Took 3 lines. Well, actually, when I put the braces in, it'll take a little more. But the trick was that the first case had to be different. Now, I actually wrote that here. Here's my actual programs for that. Let me pull these two up. These were the 2 programs I wrote. That's it. Right down there. So, let's go to another page and then print it. There they are. Now I want to test it. In fact, the reason I wrote the print was I wanted to test to see if my stuff was getting in right. And I wanted a larger tree than I had before. So what I did was I wrote another routine. Now you don't have to write this one. I wrote a routine, a method, to create a binary search tree from data in a file. Here's the file, or at least the beginning of the file. I'm over here. That's the wrong one. I'll come back to that. I want to save that as starter for homework 21. And now I'm going to bring up the other one, which is tree 1. There it is. If you remember, and even if you don't, the way it was set up was that I had in each node a name and a telephone number. And I faked the telephone numbers as if they were 3. If you want to, think of them as extensions. I don't care what we use. Now I'm going to copy this over to here so you can see the file. Let's see. I think it might be better to go to a new page with that. I'm going to bring it down here. And then it's kind of small, so I'm pretty sure I can fit it in a lot smaller space simply by doing a layout, columns, at least 3 ought to work. So there you are. And you'll notice that I put a done at the end. So each name followed by the telephone number on a different line. That way I didn't have to go through the trouble of breaking it up. I didn't feel like it. It was easier to write it this way. Now the program was actually pretty easy to write. The reason it was easy to write is I'd already written most of it. The program looked like this. Where am I? Right there. I called it create from a file. And that's in here. And this has something that you also have to start looking at as something new. So I'm going to have 1 from there down. And I'm going to have trophy. And the new thing I want to show you in this one is the use of this. In a method, this is the class, the object that the method is attached to. So when in the main line over here, I use from file dot create from file. From file is a B tree. So I want to read it. Now if you look up here, a B tree is there, and it has a root that is appointed to a node. When I came in here, this, now wait a minute, I'm too far down, I gotta go up. No, it was up here. I wanted to do add note. Add note is a method. You would think I could say this dot add node, but I think for some reason it prefers it this way. So it's the tree I'm working with, whatever I've attached it to. It's very useful. You need it a lot. Now let's see if this works. There it is. Don't dwell too long on where I got the names, but I think you can get a few of them. I see Fozzie, and I see Kermit, and I see Animal, so you might be able to guess where some of them came from. And if you'll notice, they are in alphabetical order. So what I'm going to do is I'm going to send this much of this stuff to you. I yes, I should copy this. This is the output, so you can see the output. And you should get it very shortly. And as you might guess from what I did a minute ago where I used the word starter file, I have a program I want you to do, which I haven't written up in document form yet, but I will do it, I hope, very soon. Right, up here, I'm going to put the result. And that's what I got. And now I'm going to put in the program so you can see what the program looked like, the full program. So let me get all of it. And that goes right here. Now, what are you going to be asked to do? You're going to be asked to write the pre-order or post-order transversal of the tree. The printing is also called a transversal of the tree since it visits everything. And believe it or not, the entire program, what you have to change is something like 2 lines in the entire program. You have to change the name probably. You want print pre-order. You don't want print in order. But outside of changing the names of those, I think there's 2 lines you have to fool around with, maybe 3. And with braces, maybe 4. But it's very, very, very similar to in order. If you look at the algorithm I did for in order, think about how you would change it for pre-order or post-order. That's it for now. See you later.